This presentation is delivered by the Stanford Center for Professional Development.
So this is the last thing we had talked about at the end of the merge sort, right, was comparing a quadratic, an n squared sort of the selection sort variety here, to the linear arithmetic, which is the n log n time that merge sort runs in, right, showing you that really way outperforming even on small values and getting to large values, right, that gap just getting enormous in terms of what you can accomplish with an n log n algorithm, really vastly superior to what you're going to get out of an n squared algorithm. And I said, okay, well, n log n, I told you without proof, you're going to take it on faith that I wouldn't lie to you, that is the best we can do in terms of a comparison-based sort. But what we're going to look for is a way of maybe even improving on those times of merge sort by kind of one thing we might be able to do is avoid that copying of the data out and back that merge sort does, and maybe have some lower constant factors in the process, right, that can bring our times down to something even better. So the sort we're looking at is quicksort. And I think if you were going to come up with an algorithm name, naming it quicksort is kind of good marketing here, so it kind of inspires you to believe actually it's going to live up to its name. It is a divide and conquer algorithm that takes a strategy like merge sort in the abstract, which is the divide into two pieces and recursively sort those pieces and then join them back together. But whereas merge sort does an easy split hard join, this one flips it on its head and says, well, what if we did some work on the front step in the splitting process, and then that may give us less to do on the joining step. And so the strategy for quicksort is to run through the pile of papers, whatever we're trying to work at, in a partitioning step is the first thing that it does. And that's the splitting step. And that partitioning is designed to kind of move stuff to the lower half and the upper half. So having some idea of what the middlemost value would be, and then actually just walking through the pile of papers and kind of, distributing to the left and right portions based on their comparison to this middlemost element. Once I have those two stacks, I've got A through M over here and N through Z over there, that recursively sorting those takes place, kind of assuming my delegates do their work, and then the process of rejoining them is really quite simple, right? Just they kind of, join together with actually no extra work, no looking, no process there. So the one thing that actually is where all the trickiness comes into is this idea of how we do this partitioning. So I was being a little bit disingenuous when I said, well, if I had the stack of exam papers and I know that the names, range over the alphabet A through Z, that I know where M is, and I can say, well, that's a good midpoint around to divide. Given that, right, we want to make this work for kind of any sort of data, we're not going to a priori know what's the middlemost value. If we have a bunch of numbers, are they test scores? In which case, maybe 50 is a good place to move. Are they instead, population counts of states? In which case, right, millions, right, would be a better number, right, to pick to kind of divide them up. So we have to come up with a strategy that's going to work, no matter what the input, that's somehow going to pick something that's kind of reasonable for how we're going to do these divisions. There's this idea of like picking what we call that pivot, right? So given this, region, this set of things to sort, how do I know what's a reasonable pivot? We're looking for something that's close to the median is actually ideal. So if we could, walk through them and compute the median, that would be the best we could do. We're going to try to get around not doing that much work about it, though. We're going to actually try to kind of make an approximation, and we're going to make a really kind of very simplistic choice about what my approximation would be. We're going to come back and revisit this a little bit later. But as I'm going to say, well, I just took the first paper off the stack. If they're in random order, right, and I look at the first one, I say, okay, it's somebody king. Okay, well, everybody less than king goes over here, everybody greater than king goes over there. Now, king may not be perfectly in the middle, and we're going to come back to see what that will do to the analysis. But at least we know it's in the range of the values we're looking at, right? And so it at least did that for us. And it means no matter what our data is, we can always use that. That's a strategy that will always work. We just take the thing that we first see and use it to be the pivot, and then slot them left and right. So let me go through looking at what the code actually does. And this is another of those cases where the code for partition is a little bit frightening. And the analysis we're looking at is not actually to get really, really worried about the exact details of the less than and the less than or equal to. I'm going to talk you through what it does, but the more important takeaway point is what's the algorithm behind quicksort? What's the strategy it's using to divide and conquer and how that's working out? So the main quicksort algorithm looks like this. We're given this vector of things we're trying to sort, and we have a start index and a stop index that identifies the sub-region of the vector that we're currently trying to sort. We're going to use this in subsequent calls to kind of identify what piece we're recursively focusing on. So as long as there's a positive difference between the start and the stop, so there's at least 2 elements to sort, then we go through the process of doing the division and sorting. So then it makes the call to partition, saying given this sub-region of the array, do the partition. I'm going to come back and talk about that code in a second. And the thing returned from the partition is the index at which the pivot was placed. So after it did all the work, it moved everything less than the pivot to the left side of that, everything greater than the pivot to the right side. Then the pivot will tell us where the division is, and then we make 2 recursive calls to sort everything up to but not including pivot, to sort everything past the pivot to the end. And then those calls are operating on the array in place, so we're not copying it out and copying it back. So in fact, there actually even isn't really any join step here. We said sort the 4 things on the left, sort the 7 things on the right, and then the joining of them was, well, they're already where they need to be. So in fact, we don't have anything to do in the join at all. The tricky part is certainly in partition. The version of the partition we're using here is one that kind of takes 2 indices, 2 fingers you might imagine, and it walks one in from the stopped position down and one from the start position over, and it's looking for elements that are on the wrong side. So if we start with our right-hand finger on the very end of the array, that first loop in there is designed to move the right hand down, looking for something that doesn't belong on the left-hand side. So we've identified 45 as the pivot value. It says find something that's not greater than 45. That's the first thing we found coming in from the right downward that doesn't belong. So let me do that first step. So it turns out it takes it just 1 iteration to find that. And it says, okay, this guy doesn't belong on the right-hand side. Now it does the same thing, but kind of the inverse of the left-hand side. Try to find something that doesn't belong on the left-hand side. So the left hand moves up. In this case, it took 2 iterations to get to that, to this 92. So now we have a perfect opportunity, right, to fix both our problems with 1 swap. Exchange what's at the current position of left hand with right hand, and now we will have made both of our problems go away, and we'll have kind of more things on the left and the right that belong there. And then we can walk inward from there, to find subsequent ones that are out of order. So those 2 get exchanged, and now right again moves in to find that 8. Left moves over to find that 74. We swap again. And then as we just keep doing this, right, until they cross. And once they've crossed, right, then we know that everything that the left scanned over is greater than the pivot. Everything everything the right scanned over was greater than. Everything the left was less than. And at that point, right, we have divided it, right? Everything that's small is kind of in the left side of the vector. Everything that's large is in the right side. So I swap these 2, and now I get to that place, and I say, okay. So now, big things here, small things there. The last thing we do is we move the pivot into the place right between them. We know that it is exactly located right in the slot where they crossed. And now I have 2 subarrays to work on. So the return from partition in this case will be the index 4 here, and it says, okay, go ahead and quicksort this frontmost part, and then come back and do the second part. So in recursion, kind of think of that as being postponed. It's waiting. We'll get back to it in a minute, but we're going to work on this stuff. We'll do the same thing. It's a little bit harder to see it in the small, kind of what's going on, but in this case, right, it divided that because the pivot was 8 into 8 and the 3 things greater than the pivot. In this case, the 41 is the pivot, so it's actually going to move the 41 over there and it's going to have the left of that. And so as it keeps kind of working its way down, they get smaller and smaller. It's a little bit harder to see the workings of the algorithm in such a small case of it rearranging it. But maybe we'll get back to the big left half in a second here. And so now that that's all been sorted, we're revisiting the side that's advancing above the pivot to get these 6 guys into order. And taking the same strategy, pivot around 67, moving inward, doing some swapping, and then eventually kind of placing it in the right position. And so there. So I'm going to just let it finish, and we'll see it in a slightly bigger case to kind of get the idea. But very quickly, there's something very interesting about the way quicksort's working is that partition step very quickly gets things kind of close to the right place. And so now that we've done both the left and the right, we're done, the whole thing is done. Everything kind of got moved into the right position as part of the recursive part of the sorting and doesn't need to be further moved to solve the whole problem. That first step of the partition is doing a lot of kind of throwing things, kind of left and right, but it's actually quickly moving big things and small things that are out of place, right, closer to where they're eventually going to need to go. And that turns out to be a real advantage in terms of the running time of this sort, because it actually is doing sort of some quick movement close to where it needs to be, and then it kind of fixes it up in the recursive calls that examine the smaller subsections of the vector. So let me show you what it sounds like, because that's really what you want to know. So let's give it kind of. So you can see the big partitioning happening, and then it kind of jumbling things up and then coming back to revisit them. But you notice that quite quickly, all the small elements got thrown to the left, all the large elements to the right, and then the kind of process of coming back. And so the big partition that you can see kind of working across them and then the kind of noodling down. If I turn the sound on for it. So the big partition steps making a lot of noise, right? Moving things kind of quickly, and it almost appears, to hear this kind of random sort of, it's hard to identify what's going on during the big partition. But then as you hear it make its way down the recursive tree, right, it's focusing on these smaller and smaller regions where the numbers have all been gathered because they are similar in value. And so you hear a lot of noodling in the same pitch region, right, as it's working on these smaller and smaller subarrays, and then they definitely go from low to high because the recursion chooses the left side to operate on before the right side, that you hear the work being done in the lower tones before it gets to the finishing off on the high tones. That's kind of cool. Let us come back here and talk about how to analyze this guy a little bit. So the main part of the algorithm, right, is very simple in quicksort, deceptively simple, right, because all the hard work was really done in partition. The partition step is linear, and if you can kind of just go along with me conceptually, you'll see that we're moving this left finger in, we're moving this right finger in, that we stop when they cross, and so that means every element was looked at. Either they both matched over here, they matched over here, but eventually, like, you looked at every element as you worked your way in and did some swaps along the way, and so that process is linear in the number of elements. There's 1,000 of them, kind of has to advance maybe 400 here and 600 there, but it will look at all the elements in the process of partitioning them to the lower or upper halves. Then it makes two calls, quicksort, to the left and the right portions of that. Well, we don't know exactly what that division was, right? Was it even? Was it a little lopsided? And that's certainly going to come back to be something we're going to look at. If we assume kind of just the ideal 50-50 split, sort of in an ideal world, if that choice that we had for the pivot happened to be the median or close enough to the median that effectively we got an even division at every level of the recursion, then the recurrence relation for the whole process is the time required to sort an input of n is n to partition it, and then 2 sorting 2 halves that are each half again as big as the original input. We saw that recurrence relation for merge sort. We already solved it down. Think of it in terms of the tree, right? You have the branching of 2, branching of 2, branching of 2, an n at each level, the partitioning being done across each level, and then it going to a depth of log n, right? The number of times you can divide n by 2 before you run into these single case arrays that are easily handled. So it is an n log n sort in this perfect best case. So that should mean that in terms of big O growth curves, right, merge sort and quicksort should look about the same. It does have sort of better factors, though. Let me show you. If I go back here and I just run them against each other, if I put quicksort versus merge sort here, oh no, let them stop making noise. The quicksort pretty handily managed to beat merge sort. In this case, merge sort was on the top, quicksort underneath, and certainly in terms of what was going on, it was doing looks like more comparisons, right, to get everything there. That partition step does a lot of comparison, but fewer moves. And that kind of actually does sort of make intuitive sense. You think about the fact that quicksort very quickly moves stuff to where it goes and does a little bit of noodling. Merge sort does a lot of moving things away and moving them back, and kind of like as you see it growing, you'll see a lot of large elements that get placed up in the front, but then have to be moved again, right? Because that was not their final resting place. And so merge sort does a lot of kind of movement away and back that tends to cost it overall, right? A higher constant factor of the moves than something like quicksort does, where it kind of more quickly gets to the right place and then doesn't move it again. So that was all well and good. That was assuming, though, everything went perfectly. Of course, that really, given our simplistic choice of the pivot, you can imagine that's really assuming a lot, right, that went our way. If we look at a particularly bad split, let's imagine that the number we happen to pick is pretty close to one of the extremes. So if I were sorting papers by alphabet, and if the one on the top happened to be a C, right, well then I'm going to be dividing it pretty lopsided, right? There's just going to be the A's and the B's on one side, and then everything D to the end on the other side. If I got a split that was about 90-10, 90% went on one side, 10% on the other, you would expect, right, for it to kind of change the running time of what's going on here. So I get 1/10 of them over here in the low half and maybe 9/10 in the right half. Let's just say every time it always takes 9/10 and moves it to the upper half. So I kept picking something that's artificially close to the front. These sides will kind of peter out fairly quickly, dividing n by 10 and 10 and 10 and 10. Eventually, right, these are going to peter out very, very soon. But this one arm over there, where I keep taking 90% of what remains. I had 90%, then I had 81%, right? I keep multiplying by 9/10, and I'm still kind of retaining a lot of elements on this one big portion. That the depth of this tree isn't going to bottom out quite as quickly as it used to, right? It used to, the number of times you could divide n by 2, the log base 2 of n was where we landed. In this case, right, I have to take n and multiply it by 9/10. So instead of 1/2, right, to the k, it's 9/10 to the k. And it's like, how many iterations, how deep will this get before it gets to the simple case? And so solving for n equals 10/9 to the k, taking the log base 10/9 of both sides, then k, the number of levels, is the log base 10/9 of n. Kind of relying on a fact of mathematics here, though, is that all logarithms of the same value, so log base a of n and log base b of n, they only differ by some constant. Can compute if you just rearrange the terms around. So in effect, this means that you can there's a constant in front of this. It's like a constant difference, the ratio between 10/9 and 2, that distinguishes these, but it still can be log base 2 of n in terms of big O, right, where we can throw away those constants. So even though this will perform, obviously, in experimentally, you would expect that getting this kind of split would cause it to work more slowly than it would have in a perfect split situation. The big O trend line is still going to look n log n linear rhythmic in the form. So that was pretty good to know. So it makes you feel a little bit confident. Like, well, sometimes it might be getting an even split. Sometimes it might be getting 1/3, 2/3. Sometimes it might be getting, 9/10, 1/10. But if it was kind of in the mix, still dividing off some fraction, it's still doing okay. Now let's look at the really, really, really worst case split. The really, really worst case split, right, would be that it didn't even take off a fraction. It just managed to separate one. That somehow the pivot here did a really terribly crummy job, right, of dividing it at all. That in fact all the elements were either greater than the pivot or less than the pivot, and so they all landed on one side, and the pivot was kind of by itself. So starting with an input of size n, we sectioned off one, and we had n minus 1 remaining. Well, the next time, right, we sectioned off another one. So if this happened again and again and again, we just got really bad luck all the way through. Each of these levels is only making progress to the base case at a snail's pace, right? One element is being subtracted each subsequent level, and that's going to go to a depth of n. And so now if we're doing n work across the levels, it isn't quite n work because in fact some of these bottom out, but it's still the Gaussian sum in the end, is that we got n levels doing n work each. We suddenly have what was a linear rhythmic algorithm now performing quadratically. So in the class of selection sort, insertion sort, in its worst case behavior. So quite a range, whereas merge sort, right, is a very reliable performer. Merge sort doesn't care. Is it no matter what the order is, no matter what's going on, it does the same amount of work. That means that there are some inputs that can cause quicksort to vary between being linear rhythmic and being quadratic. And there's a huge difference, as we saw in one of our earlier charts, between how those things will run for large values. So what makes the worst case? Given how we're choosing the pivot right now is to take the first thing in the subsection to look at as the pivot. What's that example input that gives you this?
Sorted.
If it's already sorted. Isn't that a charmer, right? Here's a sorting algorithm. You ask it to do something. And in fact, if you accidentally, for example, called it twice, you already had sorted the data, and then you said, oh, you did something, and you passed it back to it to sort, it would suddenly actually degenerate into its very worst case. It's already sorted. So it would say, I've got this stack of exam papers. I look at the first one. I say, oh, look, it's atoms. I say, OK, well, let me go find all the ones that belong on the left side. None of them do. I say, OK, we'll put atoms over here. I'll recursively sort that. That was easy. Oh, let me look at what I've got left. Oh, look, Baker's on the top. OK, well, let me put Baker by itself. OK, let me find the other ones. Oh, no more. Right? And it would just, continue kind of doing this thing, looking at all n minus 1, looking at all n minus 2, all the way down to the bottom, right? Making no, recognizing nothing about how beautifully the data already was arranged, and getting its worst case. There's actually a couple others that come into. That's probably the most obvious one to think of, is it's coming in increasing order. It's also true if it's in decreasing order. If I happen to have the largest value on the top, then I'll end up splitting it all into everything to the left side and nothing to the right. There are actually other variations that will also produce this. If at any given stage that we're looking at a subarray, if the first value happens to be the extreme of what remains, whether it's the smallest or the largest, it could alternate, which would be kind of a funny pattern. But if you have the tallest, then the shortest, then the tallest, and then another tallest, and then a shortest. So those would look a little bit harder to describe, but there are some other alternatives, right, that produce this bad result. All of these we could call degenerate cases. There's a small number of these relative to the n factorial permutations your data could come in, right? N factorial is a huge number, right? And so there's lots and lots of ways it could be arranged. There's a very small number of them that will be arranged in such a way to trigger this very, very worst case behaviors. Some are close to worst case, like if they were almost sorted, they might every now and then get a good split, but mostly have bad splits. But the number that actually degenerate to the absolute worst case is actually quite small. But, right? The truth is do we expect that those outputs are somehow hard to imagine us getting? Are they so unusual, right, and weird that you might be willing to say it's okay that my algorithm has this one or a couple bad cases in it because it never comes up? In this case, right, the idea that your data came in and sorted or almost sorted or reverse sorted is probably not unlikely. It might be that you happen to be reading from a file on disk and somebody has taken the care to sort it before they gave the data to you. If all of a sudden that caused your program to behave really badly, that would really be a pretty questionable outcome. So let's go back and look at it just to see, though. It's kind of interesting to see it happening in. So this is against quicksort versus merge sort. If I change the data to be partially sorted and let it run again, quicksort still managed to beat it, doing a little bit more. If I change it to totally sorted, or reverse sorted for that matter, and so they look like they're doing a lot of work about nothing. And you can see that quicksort's really still way back there, right? It's has looked at the first 10% or so and is doing a lot of frantic partitioning that never moves anything, and busily kind of like traipsing its way up there. Merge sort, meanwhile, is actually on the beach in Jamaica with a daiquiri, mocking quicksort for all those times that it said it was so much better than it was. Duh, it was already sorted, you doofus, but apparently wasn't noticing. So merge sort in this case almost looked like it did nothing. That's because it took the left half, which is the smallest half, moved it off, right, kind of copied it back, and it ends up copying each element back to the same location it was already originally present in. There you go, quicksort taking its time. And in fact, if I ran it against, let's say, insertion sort and selection sort, why not? Because we can. Because my computer has nothing better to do than to sort for you all day long. So their insertion sort actually, finishing very early because it does nothing, right? It looked at them all and said they were all already in the right order. Merge sort doing a little bit more work to move everything back and forth in the same places, but in this case, selection sort and quicksort here at the bottom and selection sort at the top, doing really roughly about the same work if you look at the sum total of the comparisons and moves. And the time spent on those, right, suddenly shows that, yeah, in this input situation, right, quicksort is performing like an n-squared sort that has obviously very similar constant factors to those present in selection sort, so really behaving totally quadratically in that worst case input. If I make it reverse sorted, it's a little more interesting because you can kind of see something going on. Everybody kind of doing their thing. Insertion sort now hitting its worst case, so it actually coming in dead last because it did so much extra moving, but still showing the kind of quadratic terms, right, that selection sort and quicksort are both having, but higher constant factors there, so taking almost twice as long because it's actually doing a little bit extra work because of that inverted situation. So let's run them on something big, just because, and we'll put it back into random. Sort of things happen. So quicksort, right, just, you know, done in a flash, merge sort finishing behind it, and then ordinarily, right, the quadratic sorts, right, taking quite a much longer time than our two recursive sorts, but in this case the random input really buying quicksort its speed. Is it going to win? Oh, come on. Oh, come on. Don't you want selection sort to come behind? I always want it to come from behind. It's kind of like rooting for the underdog. Oh, yes. And yet, just remember, don't mock insertion sort, right? When it's sorted, it is the only one that recognizes it and does something clever about it, right? Quicksort, in fact, is anti-clever about it. So it still can hold its head up and be proud. That's kind of neat to know. So I kind of thinking about, like, well, what algorithms, right? There's a reason why there's 4 that we talked about, and there's actually, you know, a dozen more. It's like that different situations actually produce different outcomes for different sorts, and there are reasons that even though they might not be the best sort for all purposes, there are some situations where it might be the right one. So if you had a data set that you expected to be mostly sorted, but had a few perturbations in it, like you had a pile of exam papers that was sorted and you dropped them on the floor and they got scuffed up a little bit, but they're still largely sorted, insertion sort's the way to go, right? It will take advantage of all the work that was already done and not redo it or create kind of havoc the way quicksort would. So quicksort, the last thing we need to tell you though about is, like, well, we can't tolerate this, right? Like this, the way quicksort is in its classic form, right, with this first element as pivot, right, would be an unacceptable way to do this algorithm. So quicksort actually typically is one of the most standard algorithms that's offered in a library in a programming language as the sort algorithm. Well, it has to have some strategy for how to deal with this in a way that does not degenerate. And so the idea is, what you need to do is just pick a different choice for the pivot. A little bit more clever, spend a little bit more time, do something that's a little less predictable than just picking that firstmost element. So to take it to the far extreme, well, one thing you could do is really just compute the median. Analyze the data and compute the median. It turns out there's a linear time algorithm for this that would look at every element of the data set once and then be able to tell you what the median was. And that would guarantee you that 50-50 split. So if you go find it, right, and use it at every stage, right, you will guarantee it. Most algorithms don't tend to do that. That's actually kind of overkill for the problem. We want to get it to where it's pretty much guaranteed to never get the worst case, but we're not concerned with it getting 50-50. If you've got 60-40 or something close enough, that actually, you know, 60-40, 70-30 and was, you know, bopping around in that range, it'd be fine. So the other two that are much more commonly used, right, is some kind of approximation of the median with a little bit of guessing or something in it. For example, median of 3 takes 3 elements, and typically it takes 3 from some specified positions. It takes the middlemost element, the last element, and the front element, and it says, okay, given those 3, rearrange them to find out what's the middle of those 3, and use that. If the data was already sorted, that turns out you got the median, right? Because it was the middlemost, right? If data was just in random position, well, then you got one that, you know, at least there's one element on one side, right? And so the odds that at every single time would produce a very bad split is pretty low. There are some inputs, right, that could kind of get it to generate a little bit, but it's pretty foolproof in most ordinary situations. Even more unpredictable would be to just choose a random element. So look at the start to stop index you have, pick a random one there, swap it to the front, and now use it as the pivot element. If you don't know ahead of time how your random number generator is seeded, it's impossible to generate an input and force it into the worst case behavior. And so the idea is that you're kind of counting on randomness and just the probabilistic outcome of it managing to be such that the way it chose the random element was to pick the extreme at everything. It's just impossible. The odds are astronomically against it. And so it will a very simple fix, right, that still leaves the possibility of the worst case in there, but in a much far removed probability sense. So just simple things, right, but then from there the algorithm operates the same way it always has, which is to say, pick the median however you want to do it, move it into that front slot, and then carry on as before in terms of the left and the right hand and moving down and swapping and recursing and all that bit. Any questions about anything about sorting algorithms, the ones we've seen? What I'm going to do is some coding, actually. This is the next thing I want to show you. Because once you know how to write sorts, sort of the other piece I think you need to have to go with it is, well, how would I write a sort to be generally useful in a large variety of situations? That knowing about these sorts, right, I might decide to build myself a really general purpose, good high performance quick sort that I could use again and again and again. And I'd want to make it work generically so that I could sort strings, or I could sort numbers, or I could sort students, or I could sort vectors of students or whatever. And I'd want to make sure that, no matter what I needed to do, it was going to solve all my problems, this one kind of sorting tool. And we need to know a little bit of C++ about how to make that work by use of the function template. So if you want to ask about sorting algorithms, now is the time.
Do a bubble sorting?
We don't cover bubble sort, which is kind of interesting. It will come up actually in the assignment I give you next week, because I think it's a little bit of a historical artifact to know about it. But it turns out bubble sort is kind of one of those sorts that is dominated by pretty much every other sort you'll know about in every way, as there's really nothing to recommend it. Whereas I said each of these four have something about them that actually has a strength over the others. Bubble sort really doesn't. It's a little bit harder to write than insertion sort. It's a little bit slower than insertion sort. It's a little bit easier to get it wrong than insertion sort. It has higher constant factors, right? It does recognize when data is in sorted order, but so does insertion sort. So it's hard to come up with a reason to actually spend a lot of time on it. But I will expose you to it in the assignment, because I think it's a little bit of a sort of part of our history, right, as a computer science student to be exposed to. But anything else about? So let me show you some things about function templates. Oh, there's some numbers. I forgot to say about that. Just to say that in the end, right, which we saw a little bit in the analysis, right, that the constant factors on quicksort are noticeable when compared to merge sort, about a factor of 4, moving things more quickly and not having to mess with them again.
Quicksort in of stuff in totally random order?
Yes, they are. Yes. So it
doesn't have it picking
So it doesn't. So this is actually using a classic quicksort with no degenerate protection, right, on random data. If I had put it in on sorted data in that case, it would definitely have, you'd seen numbers comparable to selection sorts 8 hours in that last slot, right? Or you could put in some degenerate protection, right, and it would probably have in the noise a small slowdown for that little extra work that's being done, but then you would be getting n log n performance reliably across, all space of inputs.
Do degeneracy protection,
yeah.
Does it start to even out time-wise with merge sort?
No,
or does it still do
no, it doesn't. It actually it adds it's almost an imperceptible change in the time, because it depends on which form of it you use. But if you use, for example, the random or median of 3, the amount of work you're doing is about 2 more things per level in the tree, and so it turns out, yeah, that over the space of log n is just not enough to even be noticeable. If you did the full median algorithm, you could actually start to see it, because then you'd see both a linear partition step and a linear median step, and that would actually raise the constant factors where it would probably be closer in line to merge sort. Pretty much nobody writes it that way, is the truth, but you could, kind of in theory, is why we talk about it. So I'm going to show you, kind of motivate this by starting with something simple, and then we're going to move toward building the kind of fully generic, one algorithm does it all sorting function. So what I'm going to first look at is swap, because it's a little bit easier to see it in this case, is that sometimes you need to take 2 variables and exchange their values. You need to go through a temporary to copy one and then copy the other back and whatnot. Swapping characters, swapping in, swapping strings, swapping students, any kind of variables you wanted to swap, right? You could write a specific swap function that takes 2 variables by reference of the integer, string, or character type that you're trying to exchange, and then copies one to a temporary and exchanges the 2 values. Because of the way C++ functions work, right, you really do need to say it's a string, this is a string, what's being declared here is a string, and so you might say, well, if I need more than one swap, sometimes that swaps strings and characters, my choices are basically to duplicate and copy and paste and so on. That's not good. We'd rather not do that. But what I want to do is I want to discuss what it takes to write something in template form. We have been using templates, right? The vector is a template, the set is a template, the stack and queue and all those things are templates that are written in a very generic way using a placeholder. So the code that holds on to your collection of things, right, is written saying, well, I don't know what the thing is. Is it a string? Is it an int? Is it a car? Well, vectors just hold on to things, and you can, as a client, decide what you're going to be storing in a particular kind of vector. And so what we're going to see is if I take those swap functions and I try to distill them down to say, well, what is it that any swap routine looks like? It needs to take two variables by reference. It needs to declare a temporary of that type, and then it needs to do the assignment all around to exchange those values. Can I write a version that is type unspecified, leaving a placeholder in there for what, that's really quite amazing, what we're going to be swapping, and then let there be multiple swaps generated from that one pattern. So let me do this actually in the compiler, because it's always nice to see a little bit of code happening. So I go over here. And I got some code up there that I'm just currently going to comment out because I don't want to deal with it right now. We're going to see in a second. It does something else. Okay, so your usual swap looks like this. And that would only swap exactly integers. If I wanted characters, I'd change it all around. So what I'm going to change it to is a template. I'm going to add a template header at the top. And so the template header starts with the keyword template, and then in angle brackets it says, what kind of placeholders does this template depend on? It depends on one type name, and then I've chosen the name capital T type for it. It can be, that's a choice that I'm getting to make. And it says, in the body of the function that's coming up, where I would have ordinarily fully committed on the type, I'm going to use this placeholder, capital T type, instead. And now I have written swap in such a way that it doesn't say for sure what's being exchanged. Two strings, two ints, two doubles. They are all have to be matching in this form. And I said, well, there's a placeholder, and the placeholder was going to be filled in by the client who uses swap. And on demand, we can instantiate as many versions of the swap function as we need. That if you need to swap integers, you can instantiate a swap that then fills in the placeholder type with int all the way through. And then I can use that same template or pattern to generate one that will swap characters or swap strings or swap whatever. So if I go down to my main, maybe I'll just pull my main up so there's really anything in it. And I will show you how I can do this. I can say int 1 equals 54, 2 equals 32, and I say swap 1, 2. So the usage of a function template is a little bit different than it was for class templates. That in class templates, right, we always did this thing where I said the name of the template, and then in angle brackets I said, and in particular I want the swap function that operates where the template parameter has been filled in with int. That in the case of functions, it turns out it's a little bit easier for the compiler to know what you intended. That on the basis of what my arguments are to this, is I called swap passing two integers, it knows that there's only one possibility for what version of swap you were interested in. That it must be the one where type has been filled in with int, and that's the one to generate for you. So you can use that long form of saying swap angle bracket int, but typically you will not. You'll let the compiler infer it for you on the usage. So based on the arguments you passed, it will figure out how to kind of match them to what swap said it was taking. And if it can't match them, for example, if you pass one double and one int, you'll get compiler errors. But if I've done it correctly, then it will generate for me a swap where type's been filled in with int. And if I call it again, passing different kinds of things, so having string s equals hello and t equals world, that I can write swap s and t. And now the compiler generated for me two different versions of swap, right? One for integers, one's for strings on demand, and then I didn't do anything with them. I didn't print them or anything, so there's really nothing to see there, but showing it does compile and build them. That's a pretty neat idea. Kind of important because it turns out there are a lot of pieces of code that you're going to find yourself wanting to write that don't depend, in case like swap. Swap doesn't care what it's exchanging. that they're ints, that they're strings, that they're doubles, that the way you swap two things is the same no matter what they are, right? You copy one aside, you overwrite one, you overwrite the other. And the same thing applies to much more algorithmically interesting problems like searching, like sorting, like removing duplicates, like printing, where you want to take a vector and print all of its contents, right? That the steps you need to do to print a vector of ints looks just like the steps you need to do to print a vector of strings. And so it would be very annoying every time I needed to do that, to duplicate that code, that there's a real appeal toward writing it once as a template and using it in multiple situations. So this shows, there's my swap, right? It infers, right, what I meant. And then this thing basically just shows what got happened, is that when I said int a equals 4, b equals 19, swap a of b, it used that pattern to generate the swap int, where the type parameter has been, that placeholder has been filled in and established that it's int for this particular version, which is distinct from the swap for characters and swap for strings and whatnot. So let me show you that version I talked about, print. And this one I'm going to go back to the compiler in just a second, is something, let's say that I wanted to print a vector. Printing a vector is like iterating all the members and using the stream insertion to print them out. And so here it is, taking some vector where the elements in it are of this type name. In this case, I've just used T as my short name here. The iteration looks the same, the bracketing looks the same. I do the endl, and I'd like to be able to print vectors of strings, vectors of ints, vectors of doubles with this one piece of code. So if I call print vector and I pass a vector of ints, all's good. Vector of doubles, all's good. Vector of strings, all is good. Here's where I can get a little bit into trouble here. I've made this struct chord that has an x and a y field. I make a vector that contains these chords. And then I try to call print vector of c. So when I do this, right, it will instantiate a version of print vector where the t has been matched up to, oh, it's chords that are in there. You've got a vector of chords. And so it says, okay, we'll go through and iterate over the size of the vector. And then this line is trying to say C out of a chord type. And structs don't automatically know how to output themselves onto a stream. And so at this point, when I try to instantiate, so the code in print vector is actually fine and works for a large number of types. All the primitive types will be fine. String and things like that are fine. But if I try to use it for a type for which it doesn't have this output behavior, right, I will get a compiler error. And it may come a little bit as a surprise, because print vector appeared to be working fine in all the other situations, and all of a sudden it seems like a new error is cropped up. But that error came from the instantiation of a particular version, in this case, that suddenly ran afoul of what the template expected of the type. The message you get, let's say in Xcode, looks like this: no match for operator less than in standard cout vector element operator with element type equals chord t. So it's kind of try to give you a little clue, but in its very cryptic C++ way, what you've done wrong. So this comes back to what the template has to be a little bit clear about from a client point of view, is to say, well, what is it that needs to be true? Will it really work for all types, or is there something special about the kind of things that actually need to be true about what's filled in with the placeholder to make the rest of the code work correctly? So if it uses stream insertion, or it compares two elements using equals equals, right? Something like a struct doesn't by default have those behaviors, and so you could have a template that would work for primitive types or types that had these operations declared, but wouldn't work when you gave it a more complex type that didn't have that native support in there. So I have that piece of code over here. I can just show it to you. I just took it down here. This is print vector. And it's a little bit of template. And if I were to have a vector declared of ints, and I say print vector v, but this compiles, there's nothing to print. It turns out it'll just print an empty line because there's nothing in there. But if I change this to be chord t, then my build is failing, right? And the error message I'm getting here is no match for trying to output that thing. And then it tells me about all the things I can output on a string. Well, it could be that you could output a bool or a short or unsigned int, but it's not one of those things, right? Chord t doesn't have a built-in behavior for outputting to a stream. So this is going to come back to be kind of a little bit important, because I'm going to keep going here, is that when we get to the sort, right, when we try to build this thing, we're definitely going to be depending on something being true about the elements, right? That's going to constrain what the type could be. So this is selection sort. In its ordinary form, nothing special about it other than the fact that I changed it instead of sorting a vector of ints to sort a vector of some placeholder type. So it's now introduced with a template type name header, vector of type, and then in here, operations like this really are accessing a type and another type variable out of the vector that was passed, and then comparing them to see which is smaller to decide which index. It's using swap. And so the generic swap would also be necessary for this, so that we need to have a swap for any kind of things we want to exchange. If we have a template up there for swap, then the sort can build on top of that and use that as part of its workings, which is, when it comes time to swap, any two things can be swapped using the same strategy. And this is actually where templates really start to shine. Like swap in itself isn't that stunning of an example, because you think, well, whatever, who cares? It's 3 lines of code. But every little bit does count. But once we get to things like sorting, where we could build a really killer, totally tuned, really high performance, protection against degeneracy, quick sort, and we want to be sure we can use it in all the places we need to sort. I don't want to make it to sort just strings, and then later when I need to sort for integers, I have to copy and paste it and change string to int everywhere. And then if I find a bug in one, I forget to change it in the other, I have the bug still lurking there. And so template functions are generally used for all kinds of algorithmically interesting things, sorting and searching and removing duplicates and permuting and finding the mode and shuffling and all these things that, like, okay, well, just no matter what the type of thing you're working on, the algorithm for how you do it looks the same, whether it's ints or strings or whatever. So we got this guy, and as is, right, we could push vectors of ints in there, vectors of strings in there, and the right thing would work for those without any changes to it. But it does have a lurking constraint on what must be true about the kind of elements that we're trying to sort here. Not every type will work. If I go back to my chord example, right, this xy, if I have a vector of chord and I pass it to sort, and if I go back and look at the code, you think about instantiating this with vector is all chord in here all the way through here. This part's fine, this part's fine, this part's fine, but suddenly I get to this line, and that's going to be taking two coordinate structures and saying, is this coordinate structure less than another? And that code's not going to compile. Yeah.
But back when we were doing sets, we were able to explicitly say how to compare them.
Yeah, so you're right where I'm going to be, but I'm probably not going to finish today. I'm going to have to finish on Wednesdays. We're going to do exactly what set did. And what did set do? That's right. You use a comparison function. So you have to have some coordination here where you say, well, instead of trying to use the operator less than on these things, how about the client tell me, as part of calling sort, why don't you give me the information in the form of a function that says, call me back and tell me, are these things less than, so I know how to order them. So that's exactly what we need to do, but I can't really show you the code right now, but I'll just kind of like flash it up there, and we will talk about it on Wednesday, what changes make that happen. We will pick up with chapter 8, actually after the midterm, in terms of reading.